A six-story masonry building from 1890 weighs roughly a 50-story steel frame tower built today. The masonry building uses that weight to hold itself up. The steel tower uses geometry. That single difference is why cities look the way they do. Before structural steel, tall buildings were built from load-bearing masonry. Every floor added more weight, and all of it had to be carried by the walls below. The 10-story masonry building had to be enormously thick just to support what sat above them. The Monadnock Building in Chicago, completed in 1891, is the last great example. Its ground floor walls are nearly 2 meters thick just to hold up 16 stories. Any taller and the walls at the base would consume so much floor space they defeated the purpose of building up at all. The industry needed a structural system that could carry loads more efficiently. One where the weight of a building did not accumulate in thick perimeter walls, but instead traveled down concentrated paths to the ground. The steel frame provided exactly that. A structural steel frame is a grid of vertical columns and horizontal beams. The columns carry gravity loads, the weight of everything above, straight down to the foundations. The beams span between columns, supporting the floor deck and transferring loads horizontally across the grid. Both columns and beams are almost always made from wide flange sections, an H-shaped profile that is remarkably efficient. The flanges, the flat horizontal parts, resist bending, while the web, the vertical plate between them, resists shear. A wide flange section delivers high structural performance for relatively little steel. Beams typically span between 3 and 9 meters. Columns are stacked in sections 2 to 3 stories high, aligned on a regular grid. The floor deck sits on top of the beams, usually corrugated steel sheet with poured concrete on top, composite action between the two providing the stiffness for each floor plate. A steel frame is only as strong as its connections. Where beams meet columns, the joint must transfer loads from one member to the other without failure. There are two broad categories. A pinned connection transfers vertical load but allows rotation. The beam end can move slightly, which prevents moment forces from accumulating at the joint. A rigid or moment connection prevents rotation, locking the beam and column together so they act as a single continuous unit. In practice, most connections combine high-strength bolted plates for ease of erection on site with welding added afterwards for moment capacity. Bolts allow the ironworkers to assemble sections quickly in the air, bolt up and move on, while the welds complete the structural intent. The connection design determines whether a frame resists wind forces through its joints alone, or whether it needs additional bracing. Gravity loads travel straight down, but wind and earthquakes push buildings sideways, what engineers call lateral loads. A simple grid of columns and beams, connected at pins, would rack and collapse under lateral force like a parallelogram. 3 systems are used to resist this. A braced core places diagonal steel members, or concrete shear walls, in specific bays of the structure, usually around the elevator and stairwell core at the building's center. The diagonals triangulate the frame, making it rigid against racking. A moment frame uses rigid beam-to-column connections throughout, so the joints themselves resist lateral movement. Very tall buildings often use a combination: a concrete core for stiffness, a steel perimeter frame for strength, and outrigger trusses connecting the two at intervals up the height. The famous diagrid systems on buildings like the Hearst Tower in New York eliminate interior columns entirely, routing all loads through the diagonal grid on the facade. The frame is fabricated off-site, each piece cut, drilled, and marked with an erection code in the mill. On-site, tower cranes lift the pieces, columns averaging around 500 kilograms, beams sometimes more, directly into position. Iron workers receive the piece in the air, guide it onto connection bolts, and torque the bolts to specification before moving on. A productive crew on a high-rise can lift and place 30 to 40 pieces per shift. Columns are erected 2 or 3 floors at a time. Beams follow to stabilize each level before the next column tier goes up. The floor deck comes next, then concrete. As the building rises, the crane climbs with it, either by jumping externally on the structure or climbing internally through a gap left in the floor. The steel skeleton often rises several floors ahead of the concrete, fireproofing, and cladding crews below. The steel frame took the loads that masonry spread across every wall and concentrated them into a handful of columns. That freed the floor plan, freed the facade, and freed the height, and every glass and steel tower on a modern skyline exists because of that structural logic.